This Lightning44 here, and in this video, I will be reacting to How Hot is Charizard's Flame, whatever, a video uploaded by MandJTV, a Pokemon YouTuber who I'm actually subscribed to. Earlier this week, I rewatched his video because I was doing some calculations related to that in the Naruto universe, similar situation, so I thought that the equations in his video would be relevant, so I'll go find that video so we can watch it. Now let me pause my screen recorder. No, I want to pause my screen recorder. Just so you know, the intro that I use in my videos is actually derived from his intro. Why did I say Lightning44 at the beginning of this video? I changed my YouTube username to BlackTudory7. Anyway, it's time to watch this video. You should be called back.
Greetings, Pokéfans! Michael here. Check out my Valentine's Day colors! Happy Valentine's Day, everyone, and welcome to the third installment of Strange Pokemon Physics. I'm currently in a thermodynamics class.
MandJTV, if you're watching this video, you should do a Strange Pokemon Physics. I think this will be the 9th installment to a video on Boufflant. You know, the one that its Pokédex entry says it can derail a train. I'm actually going to go and find that. So here it is. White. It says that their headbutts have enough destructive force to derail a train. Black 2, white 2. If a train were to enter their territory, they would send it flying. X also says that they can derail a train. And so does Omega Ruby. And Sword just says that they can crush a car with no more than a headbutt. And if it's useful information, the mass of Boufflant is 94.6 kilograms. Okay, back to the video that you were doing. Come on.
This semester, although the test this week was horrible, so I decided to apply some of that knowledge to one of the most well-known and beloved Pokemon of all time.
Just so you know, this week that he says in this video refers to the second week of February 2015. This video is 7 years old.
Charizard. Charizard is a fire-flying type Pokemon introduced in the first generation. This badass dragon is famous for its fiery tail and shooting off flamethrowers like no one's business. However, Charizard's flamethrowers are more impressive than the anime makes them seem.
Are they really? Okay, they probably are, but that's probably not going to be relevant.
Charizard's Pokemon Stadium Pokédex entry states, its fiery breath reaches incredible temperatures. It can quickly melt glaciers weighing 10,000 tons. 10,000 tons? Quickly? If Charizard can do that, just how hot is Charizard's fire? To figure this out, we first need to figure out how much energy is required to melt a 10,000-ton glacier. For those of you
in fact, I actually wrote something on Quora. I wrote a Quora post to the All About Naruto space, then I copied the text of that and posted it on a Narutopedia community post, and I also copied the text and played it on the Naruto subreddit, in which I talk about how hot Sasori's arm flamethrowers are because we see them in the anime and completely vaporize a kunai that Sakura throws him in just 2 seconds in Naruto Shippuden episode 26, Puppet Fight 10 vs 100.
Are unaware, energy is defined as the ability to do work, which is essentially the same as the ability to do something.
For those of you who don't know, in physics, work equals force times distance.
There's all kinds of energy, such as electrical, chemical, mechanical, and many more. Food...
let me see. There's also thermal, gravitational, radiant, nuclear, sound.
Contains energy, which is why we have to eat to survive. Calories are actually a unit of energy.
Fun fact, the food calories is actually 1,000 gram calories. So it's 1,000 of the small calories. 1 small calorie is how much energy it takes to raise a gram of water's temperature by 1 degree centigrade. The food calories are the big calories. It's how much energy it takes to raise a kilogram of water by 1 degree centigrade.
So if you eat too many calories, your body won't be able to use all of that energy, and the excess will be stored as fat. The SI unit for energy is the joule. But a joule is actually a really small amount of energy, since 1 calorie is equal to around 4 joules.
That's 1 small calorie or gram calorie. 1 food calorie is 4,184 joules.
So the kilojoule, equal to 1,000 joules, is the more common energy unit used. Now back to the glacier. There are 3 states of matter: solid, liquid, and gas.
Well, actually there are more, but those won't be relevant for the purposes of his video.
In order for a substance to have its state of matter changed, whether it's from solid to liquid or liquid to gas,
Sorry, I saw
states of
something on my
matter,
screen.
solid, liquid, and gas.
I thought I
In order for a
saw some
substance
dirt
to
on
have
my
its state
screen.
of matter changed, whether it's from solid to liquid or liquid to gas, it has to have its temperature raised, and this is achieved by the input of heat energy.
Thermal energy.
Heat is a kind of energy that only occurs when crossing over a system boundary, and it occurs when the 2 objects interacting are of different temperatures. If the object is a solid, like our glacier, the input of heat energy will raise the object's temperature until it reaches its melting point. The melting point of a substance varies with the pressures exposed to. We'll assume that the glacier is experiencing normal atmospheric pressure, the pressure you're experiencing right now, so its melting point is 32 degrees Fahrenheit, or 0 degrees Celsius. The formula for heat energy transferred to an object is Q equals mc delta T, or Q equals mcat. Q is the amount of heat energy, m is the mass of the object, delta T is the change in temperature the object experiences, and C is the specific heat capacity of the substance, or basically the object's resistance to changes in its temperature. For example, an object with a higher specific heat capacity will require more heat energy to have the same temperature change as an object with a lower specific heat capacity. Now back to the glacier. Ice's specific heat capacity is 2.108 kilojoules per kilogram Kelvin,
which is half the specific heat capacity of water.
The glacier's mass, converted to kilograms, is over 9 million kilograms, which is quite...
Make a note.
What do you want it to say?
9,071,847.
Okay, I created a note.
bit. As for delta T, I estimated that the glacier's average temperature would be around negative 13 degrees Celsius.
Convert 10 tons to kilograms.
The answer is 9,071.85 kilograms.
I said 10 tons. It's actually 10,000 tons.
Taken from this chart of glacier depth versus temperature for different months of the year.
Interesting.
The link to this paper is in the description. The temperature of a glacier varies with its depth, but negative 13 seemed like a good average number. Calculating with Q equals MCAT, getting this glacier's temperature up to 0 degrees Celsius would require 250 million kilojoules of heat energy. But wait, there's more. When a substance reaches its melting point, it doesn't all instantly melt at once. It actually requires more heat energy to be inputted, and this energy goes toward breaking the molecular bond.
In fact, you'll find out later why I asked Siri on my iPhone to save a note of the glacier's mass.
And actually changing the object's phase, as opposed to raising its temperature. The temperature remains constant during this process, and once the substance is completely melted, its temperature will start to rise again as more energy is added. The energy required to change a substance's phase is called latent heat, and the latent heat of fusion, so the solid-liquid boundary, for water is 334 kilojoules per kilogram. So in addition to the energy required to change the glacier's temperature, this glacier will require an additional 3 billion kilojoules to totally melt. So to change this glacier's temperature and completely melt it, it will require 3.3...
I'm going to make a note of this. Make a note.
What do you want it to say?
3,278,601,793.
Okay, I created a note. 3,278,601,793.
You'll find out why I made a note of that later.
3 billion kilojoules kilojoules.
2.3 billion
Do you
kilojoules.
realize how much energy this is? This is equivalent to almost 800 tons of TNT. It's around 2 times the amount of solar radiation that hits Arizona in a day.
I'm actually from Arizona.
It's around 1.4 billion Big Macs. So Charizard has to transfer an absurd amount of energy into that glacier to melt it. And if Pokemon obeys the law of conservation of energy, it also means Charizard has to eat a hell of a lot of food to do it. But we don't really care about Charizard's diet.
I was getting some paper to do math. That's why I paused the video and my screen recorder.
How hot does its fire have to be? Let's assume Charizard's fire transfers heat via convection, which is a gas or liquid, a fluid, flowing over a surface. The formula for this is Q equals HA delta T, where Q is the rate of heat transferred, the heat per time. A is the surface area over which the fluid is
Correct. The Q is in kilojoules per second.
flowing, and delta T is the difference in temperature between the surface and the fluid. H is
By the way, we're going to reorganize this equation so that delta T is all by itself on one side of the equal sign and equal to Q divided by HA.
convective heat transfer coefficient, which is a constant dependent on a lot of factors such as the fluid's viscosity, type, and velocity. I'm going to use a value of 0.05 kilowatts per meter squared Kelvin,
Okay. I'll write that down.
which I took from this paper that I linked to down in the description. For the surface area, I'm using a value of around 2.3 square meters or around 24.5 square feet.
So this is the source of our disagreement here. Because let me go to the Wikipedia article on the convective heat transfer coefficient and pause the screen recorder. I said pause. Okay, it says A, surface area where heat transfer takes place, square meters, which I assume to mean the surface area of the glacier. And obviously,
Which is the area of a circle whose diameter is Charizard's height. For the surface area, I'm using a value of around 2.3 square meters or around 24.5 square feet, which is the area of a circle whose diameter is Charizard's height.
I'm going to use the surface area of the glacier. Let me pause the screen recorder. So I guessed it was the surface area of the glacier, so the glacier is mass is 9,071,847 kilograms, and since the density of water is 1 kilogram per liter, the volume is 9,071,847 liters, which is 9,071,847 cubic meters. The cube root of that, and I'm assuming that the glacier is a cube because that's the only thing I know how to calculate for. I asked Safari what the cube root of this number was, and I got 20.856. Then I asked Safari for the formula of the surface area of a cube, and it popped up on google.com, so I just entered this as the value for the edge, and it gave me this area. So I'm going to multiply that by 0.05 covertly after pausing my screen recorder again. And by the way, he says that in the video, he says that Charizard melts the glacier in 1 hour, which is 3,600 seconds. So that's why I entered 3,600. I did this divided by 3,600. So here I did the math using Michael's assumption that the edge should refer to a circle, the area of a circle that has a diameter of 5 feet 7 inches, which results in a temperature of, 7,919,315 degrees centigrade. And my assumption is that it refers to the surface area of, Dang, I did my math wrong. Oh wait, Actually, I didn't. I was supposed to do that. A refers to the surface area of the glacier, and I got 6,966 degrees centigrade. So yeah, my opinion is that Charizard's fire, while still very impressive at nearly 7,000 degrees centigrade, convert 6,966 degrees centigrade to Fahrenheit.
The answer is 12,570.8 degrees Fahrenheit.
It's still impressive, but it's nowhere near what Michael says it was.
We need to solve for one value of T, the other being the glacier temperature of negative 13 degrees Celsius. But we need to know the heat energy per time. We have the total heat energy, but we don't have the time since the dex only said quickly. So I'm gonna guess Charizard could do it in an hour.
3,600
Solving
seconds.
for temperature, this means Charizard's fire would be almost 8 million degrees Celsius.
I got it right to the degree what his prediction was.
Over 14 million degrees Fahrenheit.
Personally, I think it's 6,966 degrees Celsius, centigrade, or about 12,570 degrees Fahrenheit. Because I think the surface area should mean the surface area of the glacier in this scenario. So my calculation, assuming that A should be the surface area of the glacier, results in Charizard's fire being 6,966 degrees centigrade or 12,569 degrees Fahrenheit. By the way, the silence while nothing happened was me doing this math, but I realized that my screen recorder was still on.
That's almost 1,400 times hotter than the sun, and the
I personally think it's not hotter than, only barely hotter than the sun.
actual flames would be 1.6 billion times brighter than direct sunlight.
Is there a way to calculate for brightness? Because I think that it's only like a less than 0.1% as hot as he thinks it is.
So unless Charizard could control the intensity of its flamethrower, Ash and everyone around him would be very, very dead. So, what have we learned today, class? Well, we've learned that Charizard is far more powerful than a walking star.
By the way, that's the surface of the sun. The core of the sun is hotter than Charizard's flame, even if Michael's calculations are right.
And it's probably a good thing that Pokemon are not real. What did you...
I think that having a real Charizard would be much more survivable because I think that A should be the surface area of the glacier, meaning that the Charizard's flame is only about 7,000 degrees centigrade.
What do you think of this video? Did you learn something? What are some other Pokemon you want to see on SPP?
Bouffalant. And yes, I did learn something from this video. I learned the equations, which I applied to Sasori's flamethrower when writing my Naruto post.
Let me know in the comments below!
Okay, you want me to write a comment? I will do that right now.
that's all I have for now. So until next time, Pokefans. Gotta catch them all.
Hey look, at least I think this is a new world record, keeping about a third of making my video only about 3 times longer than the piece that I'm reacting to.